Dr. Sanskriti is a KIPAC postdoctoral fellow at Stanford University. Her research revolves around galaxy formation, evolution, and feedback. She's also enthusiastic about teaching and outreach. Thank you so much for being here today. So,
Thank you.
my first question to you is, how did you decide to become an astronomer? And what pushed you to pursue your career in this?
Well, I think unlike most of the astronomers I know, I didn't really had any plan to become a scientist, let alone doing physics or astronomy. So until I think my 10th grade, I wanted to become, an author or a filmmaker because that's the type of environment I grew up in. And then I took physics just out of curiosity and I was kind of hooked up into it.
So, you have a master's in astronomy from the Ohio State University, followed by the PhD program. So, how do you think education in the US differs from that in India? And how was your experience having studied in both the countries?
Well, so I did my undergrad in physics in India and then did my master's in physics. Although I think during my undergrad, I had already decided that I want to do astro. But in India, we don't really have any degree program for master's in astronomy. So I had to continue in physics. And, most of the countries nowadays have 4 year undergrad programs, so they can directly go for PhD after that. But since we had 3 year BSc program, we couldn't apply to PhD just after that. We had to do masters. So those 2 years of my masters in physics in India was kind of a buffer time where I was doing the degree program in physics, but I was parallelly doing some research. Almost full time in a different institute. So that is obviously very stressful because you are parallelly doing almost two people's job, but it has paid off later. And when I moved to Ohio State for my PhD program, we don't really have a separate master's program. You have to do a 2 year coursework as part of your PhD, and you naturally get a master's. So I think two main differences I found is that here the curriculum and the syllabus, those are more dynamic, so they are regularly updated and also has a lot more flexibility. I mean, we had a lot of compulsory courses in India, and some of those are not really basic courses, they are specialized, and if you're not interested in that, it doesn't really help you in long term. While here you have a lot of electives, so when you know you are not interested or you are particularly interested in something that's very specialized, you can opt for that. So the flexibility is a huge difference. The other one is undergrad research. I mean, when I did my undergrad in India, we barely had any research component. And here people have, a lot of research exposure. Many of them already have one or two papers by the end of their undergrad, which we couldn't even imagine. So that way, I think, here I found a lot of things significantly better. But, there are always two sides of a coin. So the only thing I found in India is significantly better is we always focus a lot on the fundamentals, be it physics or math or any other subject. So people often have a much better grasp of the fundamental concepts while studying in India. While here you have a much better exposure to what is happening currently and how you can apply your knowledge. So that's the difference.
I think you get a lot of field experience in the US by doing research, whereas your concepts are very well cleared in India, as you said, the foundations.
Right.
Um, so, what are your memorable moments from your astronomy journey so far?
Well, I have, I think, a lot of memories and I would say turning points. In fact, deciding to do science and then physics and astronomy, all of these happened quite suddenly. I didn't really have any, pre planned thing as such. But I think each of the internships I did during my bachelor's and master's, I have a lot of memories from. My first experience was in GMRT, Giant Meter Wave Radio Telescope. It's in Pune. So that's a world-class facility, and especially in radio astronomy, India is one of the leading countries. So I did my first internship there, and coming from a very theory-heavy physics background, that internship itself was like a very steep learning curve because it's very instrument-focused. You have to learn a lot of new things, and um, staying in a very different place. I mean, radio telescopes are always very far from localities. So, getting used to a very different lifestyle and working style, that was a very different and also a difficult experience. But in the same time, I was like, if I can do that, I can do anything else. So, that way, I think my first research experience was a really special one. And all the other ones I did after that, I would say, I mean, I have learned a lot from all of them, be it in theory, in simulations. I had tried very different things in all of the different projects. But I think the first one is the most memorable one.
I think, as you said, by going the field and understanding how it's really done, I think that captures your interest, knowing that this is how it's done, and it's very different from what you're taught in a class if you go and actually do the work by yourself out there.
Okay.
How is research conducted, and how do you ensure your results are valid and not affected by the constraints of your data or the methods you have used?
Well, I mean, it depends on the type of techniques you are using. For example, in theory or in observation and in instrumentation, the techniques are widely different. Because in theory, it often happens that you are hypothesizing something. And in peer theory, it doesn't always have to be valid by the observation. It is kind of ad hoc. It is based on whatever the mathematical and physical foundations are there. And in instrumentation, it is mostly engineering focused. And in astronomy, often people build up telescopes depending on the type of science they're trying to solve. It's not like arbitrarily, I'm interested in something, let's make something. It's not like that. So there is a proper science goal that, okay, we have these open problems, we want to solve them. And for that, we need to have certain type of technology. And then people try to build up that. Since I work on observation, I'll probably go into more detail in that. So observations, again, depend on what type of observations you are doing. One type of observation is, we call it pointing observation, which means you take a telescope and direct it in a particular direction in the sky and try to see what is happening there. Now, depending on what you are interested in, planets, stars, galaxies, whatever, depending on where you expect that object to be, you point your telescope to that direction and study it in detail. And the survey type of observation, which is slightly different, that is kind of pre-planned that, okay, you want to survey a large area in the sky, say half of the sky. And then you have to have a design that, okay, this is how my whole observation will be set up, that this is how the telescope will move, and I will observe, say, millions of galaxies or billions of planets, something like that. That is a more pre-planned things than pointing observations. And the first stage is obviously to get the data. And the data is kind of like the ultimate truth. Whatever it tells you, it tells you. It's not like it has to be according to your expectation. So sometimes we have like serendipitous findings. We didn't expect, but we found something. And sometimes we find what we expect, but there is an important stage of interpretation. So it's not like just what you find, it's also about what you learn from that, like physically or chemically, what does it tell you? Or what you can't solve with that data, and now you need more data to solve the next stage and things like that. So the type of observation I do, it is more like pointing observation, where we, look toward a single galaxy and observe for a long time and try to see if we can see the signal. And as I said, there are other type of observations where people will probably have many, many terabytes of data, billions of galaxies, but there they get very average properties of the objects. While what I work on, it's more like smaller number of objects, but very detailed. And they are very complementary to each other.
That sounds really interesting. In a way, the data leads you to the truth. You can't assume anything before you know what the data tells you. So, based on this, could you briefly describe your current research work and what exactly is it that you're trying to study?
Right. So I am working on a very new field in astronomy. In fact, it is, I would say, if I just tell you the acronym, you might not recognize it. It is as new as that. So I work on circumgalactic medium or CGM, which basically means galactic halo. And what it exactly means is the gas outside the disk of galaxies. I mean, what we mean by galaxy is very subjective. A lot of people, if you ask them, they will just say the disk of galaxy is the whole galaxy because they work on mostly stars or the gas in between stars. And that's what the disk is made of. In fact, if you like search for, galaxy image in Google or most of the telescopes, you see the disk. That's like the brightest, most beautiful part of galaxies. But that's only a subset. There is a large amount of gas outside that disk that's hard to see. And I mean, obviously, as observers, we usually try to see that are easier to see. I mean, why not? We always start with easier problems. So for a long time, we have neglected this, vast amount of gas outside the disk that has very weak signal, very hard to see, but they play a crucial role in galaxy formation. So if you just study the disk, you can't solve everything. You need the other part, other subset of the galaxy. And there is a nice analogy to explain why this is important. So if you imagine, say, a football or a basketball, you roughly know what's the size of it, right? Now think of a coin, like a normal coin. And that's significantly smaller than the basketball, right?
Yeah.
Now that coin, that's like a disc, if you keep it like, say, heads up or whatever. And that's the galaxy disk. It is that small compared to the galaxy halo, which is like the basketball. Now, if you imagine keeping the coin at the center of the basketball, you have a large amount of empty space between the disk and the basketball. That looks empty because we can't see it. But since there is a lot of gas, it kind of fuels the disk of galaxy, and that fuel helps to form stars. So if there is no galactic halo, you can't form stars. It's like the fuel tank. But also, that's the first stage. Like if you think chronologically, now stars form, at some point they die and they explode, they throw out the metals they had formed, and now they leave the disk. And when they leave the disk, where do they go? They again go to the galactic halo. So that apparently empty space, that fuels the star formation, but when stars die, that gas and metal, they come back to the halo. So there is a cycle of gas coming and going away. But if you only look at the disk, you can't see rest of the process happening. And my research focuses on this cycle, like how gas is coming to the disk and how it is leaving the disk. And by studying these two factors, we are trying to understand a lot of things we couldn't solve just by studying the disk. And if you want like a slightly more technical term, there are terms like missing mass problem and missing metals problem and missing accretion problem. Basically, a lot of things are missing if you just study the disk, and those missing stuffs could be in the galactic halo. And some of these are not super hard to understand. For example, missing mass basically means, you know about dark matter, right? You have heard about that. And you also know about normal matter, like the matter we are made of.
Yeah.
And from cosmology, we already know what amount of normal matter and dark matter we expect in any system. But if you look at the galactic disk, we find a lot of normal matter missing. And the question is, where could that matter be? One option is the galactic halo, because that's like the most, obvious or the simplest option. But we need to observe the halo to see if the gas is actually there. Is the missing mass really there, or there are more complicated problems? And the missing metals is basically, you might already know that astronomers call everything other than hydrogen and helium as metals because they are produced inside stars. Now, if you know how stars form metals and then you observe stars, ideally you will expect that you will find all the metals because there are stars, how they're forming metals. But actually, we don't find all the metals in the disk. So again, the question is, where are the metals going? Are they leaving the disk and joining the halo, or don't we understand how stars form metals? Both are possible, but one possibility is seeing the galactic halo. And the missing accretion is related to how galactic halos kind of supply the fuel to the galaxy disk. So here also there is a nice analogy that suppose you are cooking something. Star formation is basically like cooking. You have molecular clouds, you form stars. So you have certain amount of ingredients and you make certain amount of food from that. Now, neutral hydrogen, which is everywhere in the universe, it is like the most abundant thing in the universe. That's like the raw fuel. And molecular hydrogen is like the, ready-made fuel. It's like a processed fuel. And then you cook the food. Now, the second part, like from the processed to food, that part is kind of understood. But the previous part, like how from raw fuel you go to processed fuel, we don't understand that yet. Now, again, always astronomers try to start everything from a very simplistic point of view. That let's assume everything is 100% efficient. So you have a certain amount of raw fuel and you make that exact amount of food. Like everything is happening perfectly. So whatever amount of supply is coming, that is converting to stars. That's the maximum you can have. But if it is less efficient, you will have a larger amount of food, but smaller amount of food because the stars are not forming as efficiently as you expected. But what we see is the reverse. Like stars are forming at a larger rate than the fuel is being supplied. And that sounds like a paradox because you are not supplying the fuel, then how are the stars forming? And that's called the missing accretion problem. Accretion basically means, accretion is a particular way fluids flow. And one of the easiest way to explain is how flushes work in commodes. You have seen the vortex of water. It's exactly that process. Now imagine that happening at a huge galactic scale, a lot of gas coming in that way. So it's called missing accretion because gas comes through a process called accretion. Now the question is, if we have a lot of fuel, like the raw fuel missing, where could that be? One option is that it could be in the galactic halo. Maybe we haven't, we have overlooked it for a long time because we were just looking in the disk. So now we are leading a project to see if we can find the missing fuel in the galactic halo. So that's my research.
It sounds really exciting, and you started with it's a new field, and the fact that there's so many questions, and it all comes back to the halo and how we have missed out on so much information we could have gained because we just overlooked this huge part of the galaxy. That's really incredible. So, Could you share a story about a particular scientist or a mentor who's had a significant impact on your academic journey?
Yeah, sure. So I think most recently, my PhD advisor, since I have been working with her for like 5, 6 years. So, in terms of the duration and the amount of impact, she had a huge influence on me. And she had also done her higher education in India and then moved here. So we have kind of like a common background and we can easily relate to things which maybe many other people couldn't. And also, we agree on a lot of academic things very easily. So that makes it easy to work with her. And I think one of the main things I learned from her is how to kind of think very practically. I mean, we always start with passion and kind of a romanticism that, okay, this sounds very fascinating. Let's just solve everything about the universe. That's great. I mean, obviously, you have to have that passion to drive you in the long run. But also, it's your job, which means you're getting paid and you have to deliver some of your work in a certain time because you are not being paid just for your passion. That could be your hobby. So you have to have a very, practical and pragmatic approach to finish up your job. That, okay, I have been given this fellowship. I'm like getting this for 5 years. So I'll design a project that I can finish in 5 years, not like something random that I just find interesting, but I couldn't solve. So that practicality is a very important, not just in PhD, but in the long run. And also like how to find, kind of more feasible projects that are connected to other people's work. If you are working very isolated, then it doesn't connect to other people's interest. You are probably doing great, but it's just great in itself, not that it is impactful for others. So unless you have a very good, like network of different projects with different people, it's very hard to survive in a long run. So that's something I learned from her. But I would just briefly mention that, again, in my first research internship, I learned a great thing from my advisor. He is actually an engineer. I mean, his whole training has been in engineering. Now, I was from physics, and in India, we are usually taught more about theory than experiments.
Hmm.
So he told me something very fundamental, that physicists often learn a lot of things, but don't learn how to apply that. And engineers are in the other side where, whatever they learn, they know very well how to apply or where to apply or how much to apply. So when you are coming from physics to astronomy, you have to kind of bridge that gap. And starting from that first project, I have always tried to keep that in mind.
That's really nice to hear, in a way, how your PhD mentor ha had influenced the way you think about your career so much. And I think that's advice that every researcher needs to hear when they're entering, to look at it practically. That yes, there's the passion, but it's also something you need to deliver as a career. Um, Finally, what do you think is the best part of being an astronomer?
Well, I think the best part is that, one is I can work on what I really enjoy. So it doesn't always feel like a job because, we don't really have that pressure of delivering something we don't necessarily like. It's more like you are passionate about something, but you can also balance that with whatever is required. And in terms of the bigger picture, I think, since we're all residing in the universe, the best thing like you can think of doing is learning about the universe, solving the mysteries of the universe, and telling other people about that. It's not like you always keep it within the community. So I think both from a scientific and a philosophical point of view, I couldn't think of a better career.
Thank you so much, Dr. Sanskriti. It was an incredible time talking to you. I learned a lot from this conversation, and I hope my audience did too.